Hello, my name is Ryan Bucker, and today we're going to be talking about Lidar and its application in forestry and geography. I have a slide presentation prepared. I don't know how to put this up on the video, so I'm assuming that you're following along. I will give you a next slide cue. Next slide. What is Lidar? Lidar is light image detection radiation, where essentially you're sending a beam to a target, receiving that beam, and measuring the time distance that it took for it to happen. This equation can be expressed as distance is equal to c times the time it took over 2. You're dividing it by 2 because the light had to travel there and come back. Originally, it started off as a space tool for ships to be able to measure to the other ships and see what their distance in space is, because they obviously can touch each other. Essentially, the beam would go to a spacecraft, bounce back, and they would slowly measure the position as it came in. There are a few different types of LiDAR systems used commonly today, but primarily we're going to be talking about aerial LiDAR units. There are also stationary units and mobile units that operate from the ground and are also very capable. But the advantage of aerial units is they can collect a lot of data very quickly. The first type is a scanning beam system. It essentially has a single length of laser, and as it passes over that length of laser, scans a 2D map. Finally, once you have all your data points, it's stitched together by computer software. There's a couple problems with scanning beam systems. First of all, they have a max range, which is the speed of light divided by 2 times the frequency. You can tell that the limiting factor here is obviously the frequency of the laser beam being produced, and when LiDAR started in 1995, that was the main limiting factor. Nowadays, we have a lot more access to cheaper and better lasers, so this isn't as much of an issue. The second kind of main LiDAR system is a flood lamp system. Instead of sending a single beam across the thing, it essentially takes a flood or a big area of light, and it captures it on a photodiode, and then the internal system scans individually the pixels to create the image. The difference between these two is that scanning beam systems take time to scan their entire surroundings, so they have an FOV, their field of view, and they slowly scan through that FOV as the aircraft is flying. This can provide some kind of error because as the aircraft moves in the air currents and vibrates and just naturally might come off course, this can provide error in the data because you'll get blotches and smears and motion blur. A flood lamp improves upon this concept because it takes all of the data at one point in time. It essentially can get rid of a lot of those problems of motion, and when you're attached to the bottom of an airplane like these LiDAR systems are, that's a huge problem. The most recent development in our things is a spatial light modulator system. It's a kind of a combination between scanning and a flood lamp system. Essentially, you are still scanning an area, but you're taking these really focused floods of individualized space, so you get a much higher image resolution, but it comes at a cost, and we'll talk about that a little bit later. Next slide, please. Some of the applications of this LiDAR that I've touched on primarily are the forestry and the geography. In forestry, it's been used by the Canadian government for a long time to measure the density and height of trees. They can use this data to look at where there might be potential fire hazards or where they need to go in and cut down old timber. Another application has been used in the Amazon rainforest. It's an incredibly dense ecosystem, and it's really hard to get people and explorers out there to go see these locations. Using LiDAR, they can basically eliminate the foliage almost completely and look at the underlying terrain. It also allows for the identification of these above aerial features that would be really hard to identify from the ground, such as kind of roadways, sewages, town squares and such, where you can see the imprint of these big cities, but on the ground it would just look like a mound in the dirt. But it's very clear once you eliminate the foliage and you look at it from above. Next slide, please. Some of the technical advantages of using LiDAR over, say, traditional satellite images are exactly what I just said. it can kind of eliminate the foliage. Whereas if you see in this picture here on the slide, all you see is tree coverage. But with LiDAR, you would be able to actually see the hills and get rid of that dense brush. Both satellite imaging and LiDAR suffer from similar problems, such as the phase integer ambiguity problem, where when you send out a laser signal and receive it, it's very easy to tell where you're at in the current transition of the wavelength, like what fractional percentage you come back to, but it's actually very difficult to find how many of these wavelengths happened in between. And one of the ways that LiDAR is able to penetrate the structure is using the Beers-Lambert law, where you measure the intensity of the receiving light, and based on the absorptivity, the molar absorptivity, the concentration of that element, and the thickness of the foliage, you're able to map back the density of that brush, the distance of that brush. Once you put together these incredible data sets, you can build these amazing 3D maps. And that is the true advantage of LiDAR. Next slide, please. Advancements in LiDAR technology, we already talked about SLM, which is essentially taking these really focused little bursts of images, unlike a traditional scattering method where you take this large sweeping. One of the problems with this is that you're left with a lot more data points, and unlike with the previous methods where you can actually process them really quickly, these require lots of skill and lots of really advanced computer algorithms. Next slide, please. The future of LiDAR is that we'll need to improve upon the data processing process. And this will come in with things like AI and just people that learn the skill and the trades better. Better computer models will help a lot. As far as what will happen once we get there, we'll be able to find more of these hidden structures and things that we didn't even know were hidden beneath the foliage. You can see in this picture here, this is a picture of a hidden city found in the Amazon that they were completely unaware of because it's completely covered up by vegetation, but when you remove that away, it's obvious. Next slide, please. Some of the key takeaway: LiDAR is essential for modern mapping and environmental studies. It really provides a clear advantage over satellite imaging, but the problem is that sometimes when you take these images on an overhead LiDAR view, you're not sure what it actually looks like in the real world. So we need individuals that are willing to go down and test these hypotheses, look at what we've LiDAR imaged and determine this is that or this is not that. We can depend on locals, and we need their help to find these locations often, but people that live there have a vesting interest, and so we almost need people from outside of the area to go in and confirm these discoveries. Thank you very much. This has been my presentation on LiDAR scanning.